It's now the time for our interview. We're going to be interviewing Dr. John Ashton, and today he's going to be sharing with us a little bit about the chemistry of life, and particularly what is mirrored image life. It's something that a lot of people are concerned about. It's a new word that's circulating around. Dr. John, thank you so much for joining us on the Breakfast Show this morning. It's great to have you.
Yes, good morning.
Dr. John, tell us a little bit about the topic of today. What is it, mirror image life, and why should we care about, and how does it work? That's I guess what we like to learn from you.
Yes, okay. So this is a fascinating topic that perhaps was mooted by a very clever guy, Charles Dodson. A lot of people would know him as the author of Alice in Wonderland. I forget what his pseudonym was, but his real name, he was a maths tutor at Oxford. And he wrote, of course, the interesting story of Alice in Wonderland. Now, it's quite interesting. Alice has a cat, and she goes through the looking glass mirror, and so she goes into a world where everything is inverted. So, if when you look into the mirror, you're right, and you hold your right hand up, it looks like your left hand. Mm-hmm. And so as she's exploring this world, her little cat comes across a bowl of milk. And she says, perhaps looking glass milk is unfit to drink. And this is a very interesting concept that maybe milk, that was the mirror image, or the molecules in milk were the mirror image, would be unfit to drink. And that happens to be true, because one of the components of milk, for example, is the sugar lactose.
Dr. John, sorry to interrupt you, but the call is a little bit cracked. All right. Sorry about that, Dr. John. I think that we have you a better connection now.
Oh, okay. So as I was saying, so Alice, in the book Alice in Wonderland, which, as I said, was written by Charles Dodson, who was the real name for Lewis Carroll, who wrote the book. So they've gone imaginarily through the mirror, so where everything is reversed, is a mirror image of everything. So it's laterally inverted. And the cat sees a bowl of milk, and Alice comments and cautions her, maybe
fit to drink. And as I was saying, it turns out that it is, because it contains, we know that there's milk sugar or lactic acid in milk. Lactic acid is a molecule that can come in both a right-handed and a left-handed form. And offhand, I forget which form is safe. It might be the L form, which means L for left or levose, and the D form is for the right hand, dextrose. And so what happens is that the other form, the right-handed form of that molecule, is toxic, is poisonous. So this is a very, very interesting property. So it's sort of like you can get molecules. If you can imagine a molecule in the shape of your right hand, a molecule in and each of your fingers represents an atom. And you can imagine if you held that up to the mirror, you would see your left hand. So it's still the same atoms. It still has the same chemical formula if you were to write it down on a piece of paper, but it has a different physical structure. In other words, the molecule has a different structure. The atoms, although they have the same formula, are arranged in a slightly different structure, so one is the mirror image of the other. And what we find in nature is that, and this is the wonderful thing, in nature produces only either right-handed or left-handed molecules of a particular molecule. If we try to make that molecule in the laboratory using a chemical reaction, we will get what is called a racemic mixture, which is exactly 50-50 mixture of both. So we always produce both sides. Now, another classic example of this is the amino acids that are in protein. So when we eat a high-protein food like meat or fish, nuts, these sort of, and legumes that are high in what we call protein, the proteins are made up of compounds called amino acids. Mm-hmm. And these compounds then become the building blocks of the different cells and structure in our body or any animal's organism's body. And these come in different forms. And from memory, going from memory, all the ones in nature that we use, they'll be all the same. They'll be either all left-handed ones. I think the left-handed ones are the ones that are non-poisonous. If we had the right-handed ones, they would be toxic. And the classic example of this is that, from memory, the active poisons in snake venom are simply the right-handed form or the opposite form of amino acids.
Oh, really?
And, so in one form we can eat them in our nuts and seeds and so forth, but in the opposite, in the mirror form, they are toxic.
That is crazy. So
it's fascinating.
In nature, all of these molecules are produced always in the same orientation, and this is the orientation that leads to life. In laboratories, we can produce both, but so. What is the mirror life image? What would that be like? Because we're talking about mirrored amino acids and molecules and sugars. But what about, and they are toxic if they're not in the right orientation? But what about what is mirrored image life then?
Oh well, it's just life that is made up where instead of using the left-handed amino acids, assuming that's the ones that are normal, you make life using the right-handed amino acids.
And why is that a concern to scientists? Why are they pointing out that this can be probably one of the great existential threats to humanity?
Okay, so if they could make bacteria, for example, that have these components in them, and then they get into us and become part of our food, but our bodies are used to only the left-handed one, then they'll become toxic to us. They'll become very poisonous.
All right. So, for example, let's say that we are infected with a bacteria that is, has all of the proteins, all of the molecules on the opposite side. Doesn't our bodies and our immune system just respond to them as per normal, or they somehow bypass and they bug out, so to speak, our system?
Well, this is it. They can exchange, and this is where scientists are worried, and this is why the camp is split into two groups. I mean, how far could this go? The problem with bacteria is that if we somehow were able to, and I'm not sure how far we've got with this, but if they are able to, synthesize viable life, and they're starting to do this, synthesize bits of DNA and so forth, and then link it together using enzymes in live yeast and this sort of thing, and therefore assemble DNA components. One of the things is that if they do this using, as I said, mirror image molecules, and these get out there and we make a viable bacteria, and this viable bacteria escapes, and then, they have the capacity to multiply and survive, where does this all end? So one of the other aspects, of course, that they argue against this is that if we can produce some of these sort of cells, maybe we can kill off cancers and things like this and use it in a positive way. There's a couple of other interesting implications to this, and one is the area that I'm quite interested in. That when people talk about the evolutionists, claim that, life formed from non-living molecules and this sort of thing. This, it's called the chirality problem. If you're looking at straight chemical reactions occurring in nature, they're going to produce 50-50 mixtures, half of which is going to be toxic to life. So this is a major hurdle for evolutionists to have some form of life forming from chemical reactions. The only systems that can produce pure left-handed or right-handed molecules are the ones that occur in existing living systems. So this is a major problem for the evolutionary model. Another classic example that applies in, say, everyday life is if you buy a vitamin D supplement. So the cheaper supplements, you'll notice that if you read the ingredient, it'll be DL-alpha tocopherol, right? And that
Correct.
D and that L telling you that it's a mixture of right and left-handed D-alpha tocopherol. But our body can only use D-alpha tocopherol. Now, fortunately, L-alpha tocopherol is neutral. It's not harmful to us, right? So not all left-handed, not all the opposite are necessarily toxic. Some of them are just neutral.
But this is saying that I'm buying a vitamin D supplement and half of it, my body's not going to be able to use. I'm actually paying for half of the stuff that that's not going to serve me anything.
I don't know what the cost system is. No, that's true. And this is another thing that frustrates me too. When often in the literature, when they do studies at the universities and that, they've chosen the cheaper one, the DL tocopherol, and they've done these studies and then they've shown, it has such and such effect or it doesn't do such and such. And I often ask them, well, why don't they buy the D-alpha tocopherol? And you can buy that, for example, Blackmore's is always just pure D-alpha tocopherol. So this is an example, but the whole concept of this mirror life, it's quite a fascinating area, and scientists are genuinely concerned if we allow this to go too far, and we actually do have an organism, say for example like E. coli, a bacteria, and then we have part of it now that has mirror image components in it. Is that now going to be far more toxic for us? And so how far does it go?
Look, I don't know about you, Dr. John, but all that idea of I don't know if we're supposed to be dominating that technology of creating life. I do not know if humanity is mature enough to be, some people call that playing God, because now you're creating life from scratch. Of course, not absolutely from scratch. You have to start with something that already exists. But, every time that these kinds of new technologies come, it makes me a little bit nervous that, hey, are we going to be creating something that can potentially kill us here?
Yeah, I agree. Yeah. And I think this is why, scientists are certainly concerned about that. And we've seen, of course, this happen in the area of genetic engineering, where we actually take genes, for example, for one organism and put them in another. As a matter of fact, one of the other aspects of this is, and it is related to genetic engineering, it is a form of genetic engineering. And we know that, some of the major food poisoning bacteria that we have to worry about now, they haven't been deliberately genetically engineered, but they've been accidentally genetic engineered. And what happens there is you have a fairly harmless bacteria like E. coli, and they colonise in the bowel. They're a large part of our poo, this sort of thing. But if we put into that bacteria the genes to make a toxin, that bacteria then becomes very dangerous to us. And that's how a number of children were poisoned in the Garibaldi sausage case in South Australia a few decades ago. What had happened was an E. coli had been implanted with a really serious toxin. I think it was E. coli H0111. That's a particular strain of E. coli, had actually formed by taking on board this toxin, and those children became poisoned. And that bacteria had a toxin that was so powerful that it just slowly destroyed components of your body. So those children became diabetic, and some lost, other organs or suffered brain damage. So once we get into this mirror image life forms, it certainly is scary.
It's a bit of a worry. Well, thank you, Dr. John, to helping us understand a little bit more about this concept that people are starting to talk more about.